Thank you so much to both Erics for that very kind introduction, and thank you all for being here. I am just delighted to be here with you tonight and to give this talk. I've been looking forward to this for a very long time, and I'm very excited to share some of the work that we've been doing in my group at Yale and other geophysicists throughout really the world, looking at the structure and evolution of the North American continent. So I'm going to motivate this talk by showing a map. And this is one of my favorite maps. I actually have a poster size of this map up on the wall of my office. So this, of course, is a map of the world. The colors here, the greens and the yellows, these show topography on land. And then the blue colors show what we call bathymetry, which is basically the topography of the ocean floor. This map also shows the locations of volcanoes and earthquakes. And I know they're a little small, so it's a little tough to see, but the red triangles are locations of volcanoes, and the little black circles are locations of earthquakes. Like I said, this is one of my favorite maps. Every time I look at it, which I do all the time because it's on the wall of my office, I see something new and different that I hadn't noticed before. And one of the reasons I love this map is because just at a glance, it tells us two really fundamental things about the Earth, okay? The first fundamental thing, the Earth has continents. And that sounds a little bit obvious to us because, of course, we live on continents. But it doesn't have to be that way. A lot of planets, other terrestrial planets in the solar system don't have continents. So we have continents, and the reason we do is that continental crust is made of different kinds of rocks than oceanic crust. Those continental crust rocks are a little less dense, and that means that the continents kind of ride up a little higher. They sit a little higher. You can almost think like an iceberg, right, floating in the water, and part of that iceberg pokes up because the ice is less dense than the water. Now, the Earth's interior is not made of water, but it is made of rocks that can flow. So those rocks are solid, but you can almost think of it like silly putty. It's solid, but the rocks can flow. And that's the reason that we have continents. If it weren't for that difference between the rocks of the continents and the rocks of the ocean, the whole planet would be covered in water. We'd all be under the oceans, and we wouldn't be here, at least not in the form that we're here. So that's the first thing that this map tells us. The other thing that this map tells us, and again, just at a glance, is it tells us that the Earth has plate tectonics. And the reason it tells us that is because if you look at the distribution of these volcanoes and earthquakes, they're not evenly distributed all over the map. Most of them fall along the boundaries of tectonic plates. Plate tectonics is really the fundamental kind of foundational theory for the earth sciences. It is a very well-tested and well-posed theory. It was developed in kind of the late 1960s. Plate tectonic theory tells us that the surface of the Earth, and here when I say surface, I'm talking about the Earth's crust and the top part of the Earth's mantle. This is the part, and we call it the lithosphere. This is really the part that behaves as a plate. So the Earth's surface is broken up into 12 major plates and then another couple dozen minor plates. And these plates are moving around with respect to one another over geologic time. The plates move about as fast as your fingernails grow, which is not very fast, but of course, over tens and hundreds of millions of years, billions of years, these plates, they really get around. And I'm going to show you that here. This is a model of plate tectonic motion over the last billion years of Earth's history. The Earth is 4.6 billion years old, so this is actually only about a fifth of Earth's history. So the numbers up here at the top, these represent time, so this is going to play through a couple times, but it starts at about 950 million years ago and then goes through to the present. The yellow splotches are the continents. So you can see the continents are bopping around. It's like they're having a party. They're coming together, moving apart. And then as this goes to the present, the continents move to their present day positions. The red lines here with the little teeth, these are subduction zones. So this is where oceanic plates are sinking back into the mantle. They sink back into the mantle because they're heavy, so they're dense. And all of this motion gives us the motion of these tectonic plates with respect to one another. So continents, I've mentioned already several times. several times. Continents are a really important and fundamental component of the plate tectonic system. And they're important for plate tectonics. They're, of course, also important for humans, right? Humans, animal life evolved on continents, or at least land-based animal life evolved on continents. Continents are also where we get our resources. Raise your hand if you have a cell phone in your pocket or purse. Come on, I know that's everybody, right? The lithium and cobalt and critical minerals that go into making the batteries for your cell phone, those come from deposits of critical minerals on the continents. So the question that I'm going to pose in this talk is, what do these continents look like deep down? You know, not right here at the surface where we are, but deep in the earth. So this is kind of a cartoon view of an idealized continent. So here's the continent here. On one side, we have a subduction zone, and again, that's where we have oceanic lithosphere, the oceanic plate that's sinking back into the mantle. Over on this side, we have a mid-ocean ridge. That's where the plates are moving apart, and new oceanic crust and mantle lithosphere gets created. And then in the middle, we have this continent. So we have the crustal part. The continental crust is about 40 kilometers thick. And then beneath that, we have what's called the subcontinental lithospheric mantle. It's a little bit of a mouthful, but basically the mantle part of the plate and the crust, that makes up what we call the lithosphere. And that's the part that is plate-like. So I've told you that this is a cartoon view of what a continent looks like deep down, and there are a few, labels on here, mostly talking about geologic ages. But you'll notice there's not a lot of detail on this cartoon about what the continental lithosphere looks like deep down. And that's partly because it's an idealized cartoon, but it's partly because the deep continental lithosphere is really difficult to study. We can't go there directly. The deepest drill hole that we've ever drilled is maybe something like 7 or 10 miles down. You're not even getting into the mantle at this point. So this is not a region of the Earth that we can study directly. Instead, we have to use indirect methods to study it. And in particular, the premise of this talk is that we can use geophysical imaging, and specifically seismology, to study the deep structure of continents. So now I want to spend a couple minutes sort of describing to you how we do this. How do we study the Earth's interior, the part of the Earth that we can't access directly, which is most of it? So up here, this is a cartoon view of what the Earth's interior looks like. So we have, of course, the atmosphere and the oceans. We have the crust, which is a pretty thin, it's like the skin on the apple, a pretty thin layer. Then we have the mantle, which is made out of solid rock, but again, that rock is able to flow, and we have convection in the mantle. And then we have the core, which is made of metal, mostly of iron. The outer core is liquid, and then the inner core is solid. So I'm quite sure that everybody in this audience has at some point in their life seen a diagram like this, maybe in elementary school, right? The crust, the mantle, the core. Now, I know this is a very intelligent audience who is spending its Thursday night. You're spending your Thursday night going to a talk about geophysics. And it may have occurred to you to wonder at some point when you've been shown this cartoon, like, how do we know that, right? How do we know that the Earth has a core and that it's made of iron and that the outer part is liquid and the inner part is solid? It's not obvious, right, how we should know that. The answer is really from geophysics, and a lot of that knowledge comes from the science of seismology. So seismologists use recordings of earthquakes at stations all over the world to understand what the Earth's interior looks like, what its structure is, and how it works. So this is how we do this. This is a diagram showing sort of waves from actually a real earthquake. This is real earthquake data over here on the right that I'll talk through in a second. This is data from the Northridge earthquake, Northridge, California, in the 90s. The idea here is that an earthquake happens somewhere on Earth, kind of like dropping a pebble in a pond. You drop the pebble and the waves emanate out from where you dropped the stone. Similarly, an earthquake happens, and earthquake waves, their seismic waves are elastic waves. They emanate, propagate out from the earthquake. We have so-called body waves that go through the body of the Earth. Two kinds of waves, P waves and S waves. And then we have surface waves that travel along the surface of the Earth. So these waves are going down, and they're interacting with all of this deep structure. And then they come back up, and they reach the surface, and we can measure them. So what is being shown, all of these little triangles over here, these are the locations of real seismic stations distributed all around the world at different distances from the earthquake. And what's being shown over here is a series of what we call seismograms. These are measurements of the Earth's ground motion. And each one of these little lines, each one of these little wiggles, shows the ground motion due to waves from the Northridge earthquake at a particular point in the Earth. Okay, so you can go along and you see each little wiggle here on one of these seismograms. This corresponds to one of these seismic waves hitting the station, okay? So my job as a seismologist is to take all of these wiggles that represent ground motion from an earthquake and turn them into insights about how the Earth's interior works. So what can we do with these wiggles? What do we actually do with the data? There are a lot of things we do. I actually teach a semester-long course at Yale about this, so you're going to get the quick version. But a lot of what seismologists do with the data actually feels a little bit familiar to us, because there are a lot of analogies with medical imaging. So, you can go to the hospital, you can get medical tomography done, you can go get a CT scan, a computed tomography scan, say of the interior of your brain, and they'll use x-rays that are passing through the interior of your body to reconstruct an image of, in this case, your brain. Seismologists can do basically the same thing with seismic waves, so we can do what's called tomographic imaging, seismic tomography of the Earth's interior. And this is a tomographic model of the upper mantle. This is a depth slice of the upper mantle at a depth of 200 kilometers down in the Earth beneath the continental US. So the way to read this is where you see blue colors. The seismic waves travel a little faster than average, about 5% faster. Where you see red colors, the seismic waves travel a little bit slower than average, about 5% slower. Now I'm going to come back to this image and talk you through what it tells us about North America, but for now I want you to have an idea that seismologists can image the Earth's interior rather like doctors can do medical imaging of the interior of our body. Okay, so in order to do this, we need two ingredients. First of all, you need earthquakes, and the Earth is happy to oblige us there. This is a map that I pulled off the EarthScope website. This is their seismic monitor. I actually pulled this off of the internet about 2 hours ago. And what you're looking at, so all of the little orange dots, those are earthquakes that happened in the past 5 years. And you can see that they really nicely trace out the plate boundaries. There are some earthquakes that happen away from plate boundaries, and we're going to get to that later on in the talk, but a lot of them are happening along plate boundaries. All of the open circles that you see, these are all earthquakes that have happened just in the last 2 weeks. And in fact, the purple ones happened in the last 24 hours, okay? So, and most of these are a magnitude 4 or bigger. Now, in the US, we have a very good catalog, so these go down to about a magnitude 2.5 or so. But as you can see from this map, the Earth gives us a lot to work with. And the reason I actually updated my slides a couple hours ago to show the latest version of this map is there was actually a magnitude 7.8 earthquake a few hours ago up in the Kamchatka Peninsula of Russia. You may remember that there was a magnitude 8.8 earthquake there about 6 weeks ago or so. This was actually an aftershock, a magnitude 7.8 aftershock to that earthquake. Now, I don't want to be flippant about this, of course, right? Earthquakes sometimes happen where there's infrastructure and where there's people, and they are extraordinarily damaging, right? And one reason to study earthquakes is so that we can prepare for and mitigate that damage. But for somebody who does Earth imaging, all of the seismicity, and most of these earthquakes never made the news, they never caused any damage. All of these earthquakes these are the sources that someone like me uses for her geophysical imaging. So we need earthquakes, and then we also need seismometers, right? We need instruments that can measure those earthquake waves. This is a map of a very important global array of seismometers. This is what's known as the Global Seismographic Network, or GSN. It's a network of about 200 very high-quality seismic stations. The data are, transmitted via satellite, so they're available in real time. When you turn on the news and you hear something like there was just a magnitude 7.8 earthquake in Kamchatka a few hours ago, the data used to detect and characterize that earthquake came from the GSN. This is also the network of seismometers that agencies like NOAA use to do tsunami warnings. So this is a very important and scientifically, kind of priceless global network. So this is one way that a scientist like me can get data to do her imaging of the Earth's interior. But individual seismologists can also go out and collect their own data, okay? And this is, as Eric said in the introduction, this is a big part of what I do. This is a picture of me in the field this past July up in Newfoundland, where we were installing a set of let's see, 22 seismometers all across the island of Newfoundland. Up in Canada, this is known as the PACMIN project, the Passive Array for Critical Minerals in Newfoundland. This is our project logo, and it conveniently also has a map of where we put in all of our seismic stations. So an individual scientist like me who's interested in, say, the evolution of the continental lithosphere beneath Newfoundland can go out and collect her own data. And so this is me standing in front of an almost completed seismic station. There's our solar panel. And if you look closely, you can see my colleague Fred, who's fussing with the electronics, probably trying to fix something down there. So in addition to global networks and then also arrays that individual seismologists go out and install, a lot of places, including the US, also carry out kind of big geophysical infrastructure projects. So a lot of countries have their own national seismic networks, including the US. But this map is a map of a geophysical infrastructure project that's very near and dear to my heart. This is a map of the EarthScope US Array project. The data collection for this project took place roughly between like 2005 and 2015. Every dot on this or symbol on this map represents an installation of geophysical instrumentation. Most of it is seismometers. And as you can see from this map, this effort really blanketed the lower 48. And actually, Alaska's not on this map, but also a lot of infrastructure, a lot of seismometers were installed up in Alaska as well. Really blanketed the US and the southern part of Canada here with seismic instrumentation. And this data set has just revolutionized what we know about the North American continent. And that's kind of where I'm going for the rest of the talk. So let's come back to North America. So what do we know about the North American continent and how it's put together? So this is a geologic map. This is a model of what is today continental North America, what it looked like if you go back 1 billion years in Earth's history. So roughly when that movie of the plates moving around that I showed, roughly when that started, okay? This is what North America looked like. Of course, it wasn't called North America then. We refer to this as Laurentia, the sort of early precursor to the North American continent. This is from work by Whitmire and Karlstrom. All the different colors essentially represent different rock types. And what you can sort of see from this picture is that the core, the continental core of North America really was sort of stitched together. It's almost like a quilt out of different pieces of continental fragments that over time got pushed together and sort of amalgamated into what is now North America. So if you go back 1 billion years in Earth's history, this is what you would see for what is now today Laurentia. And again, it's kind of the story of all these different bits of continent that sort of got stitched together. So that's what it looked like 1 billion years ago. How did we get to where we are today? Over here on the left, I'm showing another plate tectonic reconstruction, another model for what the plates were doing. This one starts, rather than going back 1 billion years in Earth's history, this one starts about 500 million years ago. The way to think about this is to imagine, it's going to play on a loop, so it'll play a few times. The way to think about this is to imagine that there's a giant movie camera over North America. North America is moving around on the surface of the Earth, and the camera is kind of following it. So we're looking at this in the reference frame of North America. So what happens, and I want you to focus especially here on the eastern side of North America, is a bunch of what we call, geologists call terrains, kind of pieces of continent, sort of get pushed onto the side of North America over a period of a couple 100 million years. This corresponds to the formation of the Appalachian Mountains. That series of collisions of what we call terrain accretion kind of culminated in the formation of the supercontinent Pangaea, which came together roughly 250 million years ago. This is playing, again, I should have said this, down here is the time frame. So right now we're at about 350 million years ago. Here comes Gondwana together to form the Pangaea supercontinent. And then right about 200 million years ago, Pangaea breaks apart. What we know today is the Atlantic Ocean basin sort of starts to form, and the continents move to their kind of present day positions. So all of this tectonic activity, again, especially over here on the East Coast, because this is a talk about the central and eastern US, gave us this beautiful geology that we see today. This is from the USGS geologic map of North America. And especially out here on the eastern seaboard, we just have this beautiful series of terrains that all got kind of smushed, that's a technical term, smushed onto the side of North America. Okay, so the story of building the North American continent is kind of this story of different fragments of continents getting amalgamated together. So that's what we know about the North American continent. How about what we don't know? This is a partial list, okay? And I know it's a little hard to read. There are a lot of unanswered questions. And of course, science is really about the questions that we don't know the answers to, right? How do the puzzle pieces that make up the continent, how do they fit together at depth? We can see the bedrock geology at the surface. What's happening in the deeper crust and mantle lithosphere? What happens in the deep crust and mantle lithosphere to build mountain ranges, like the Appalachians? What are the tectonic processes that can modify continental lithosphere through geologic time? How does the deep structure of the lithosphere relate to the distribution of intraplate earthquakes? We're going to get to that in a few minutes. Why did volcanic activity happen in the middle of North America, far away from plate boundaries in the geologic past? How does the deep structure of the lithosphere relate to the distribution of critical minerals? There's a really practical question for you. Why do different portions of the Appalachians, we just looked at that geologic map, why do they look different? What controls that? How often does continental lithosphere get destroyed? Does it ever kind of drip off the bottom of the continent and sink back into the mantle? But what about North America compared to other continents? Is North America unique, or do all continents kind of look alike? And finally, did ancient mountain ranges, such as the Appalachians, did they look just like modern mountain ranges like the Himalayas, or are there some differences? And this is just a partial list of questions that we don't know the answer to. So for the rest of the talk, I'm going to talk about some work, mostly that we've been doing in my group, but also by some other geophysics groups as well, to try to answer some of these questions. So let's come back to this tomographic image of North America, or at least of the continental US, that I teased a few slides ago. Okay, so what have we learned about the North American continent from geophysical imaging? This is kind of the continent-wide view. So again, these are tomographic images. The way to read this is where you see blue colors, the waves travel a little faster than average. Red, they travel a little slower than average. And the way we often interpret those differences is through temperature, okay? So when rocks are cold, they're stiff, and seismic waves tend to travel faster through them. So when you see blue colors, think cold temperatures. Where you see red colors, think warm temperatures, okay? So there are two figures here. One is a depth slice, and this is an S-wave velocity model, but you can do this with P waves too. One is a depth slice at 75 kilometers depth, so that's the very kind of upper part of the upper mantle, and then one is a depth slice down at 200 kilometers depth. Now the mantle is 2,900 kilometers deep, so even though 200 kilometers is pretty deep, we're still just kind of scratching the surface here. Okay, so what do we see? At a depth of 75 kilometers, we see a very clear first-order difference between the fast, cold, interior part of the continent, Remember, this is sort of the core of the North American continent. This is what we called Laurentia on that map of what North America looked like 1 billion years ago. So we see fast seismic waves, cold temperatures in the old kind of cold core of the continent. So that makes sense. And we see a lot of reds over here. Now remember, the west coast of the US is a plate boundary. This is an active plate boundary, in contrast to this part of North America, which is far away from a plate boundary today. Out here, we see a lot of slower velocities, warmer temperatures. Things are younger, they're more active. So that sort of makes sense. Now let's go down a little deeper. And so now we're down at a depth of 200 kilometers. We start to see some really kind of interesting structures. So we still see sort of to first order, more fast stuff here beneath the old core of the continent. But within that core, we start to see some interesting variations. Some places look a little faster, some places look a little slower. Well, we don't know exactly what those variations are telling us. Another thing we see, and again, I'm focusing here on kind of the central and eastern part of the US, there are two really prominent red blobs on this image, right? So there's this feature here, this feature here. So these are slow features, which might, tells us we think that they're anomalously hot. These have been very creatively named, the Northern Appalachian Anomaly and the Central Appalachian Anomaly. And these are a bit of a mystery. What is going on here? I have some thoughts that I'm going to share with you. Okay, so that's kind of the continent-wide view of this. And for the next few slides, I'm going to share 3 kind of quick little vignettes from my own research group on a few different problems, actually including the NAA and the CAA, that just gives you a flavor for the kinds of questions that we can ask and answer when we do really detailed imaging of the continental lithosphere. So first, I'm going to take you to Connecticut. So for the Yale alums in the audience, we're going home a little here. Whoops, oh, what did I just do? So we're going to Connecticut. This up here, sorry, I'm pressing the wrong buttons. This is a tectonic map of the Appalachians. So we're here in the eastern US. Up here is Newfoundland, where I spent some of my summer. This is New England. Here's Cape Cod. Here's Connecticut. And then we go down into the southern Appalachians here. The different colors on this map, they represent different terrains that got amalgamated onto North America during the Appalachians. This box here is our area of interest. This is roughly Connecticut and a little bit of Rhode Island. And this is a really interesting part of the Appalachians because you have a bunch of different terrains that are kind of sitting right next to each other. So if you want to look at how the structures, the deep structures of the crust and mantle, how they change across these terrain boundaries, Connecticut is an amazing place to look. So about 8 or 10 years ago, I, along with a couple students in my group, we deployed a network of seismometers across northern Connecticut and one over here in Rhode Island. These seismometers were spaced very closely. They were spaced about 10 kilometers apart, much denser even than the EarthScope map that I showed you before. The denser your seismic instrumentation, the better the resolution of your model. So we're looking to make very detailed images of the crust and upper mantle. And then this is over here just to remind me, to remind you, that again, we're measuring waves from earthquakes that happen all around the world and pass through the crust and upper mantle beneath the stations. Okay, so this is one of our findings. This is one of my favorite figures. And I need to say that this is work done by Yantal Luo, who's a former PhD student of mine. This is his image of what's the crust and the upper mantle look like beneath Connecticut. This is kind of meant to be a 3D diagram. So what you're seeing up here at the top, this is the bedrock geology, so the different colors are different terrains. The blue stuff is Laurentia, that's the old core of the continent, and then the reds and the greens here are different terrains that got accreted during the Appalachians. So again, we're seeing red and blue colors. This is actually not a tomography image. This is a slightly different imaging technique. Briefly, what we're doing is we're taking P waves from distant earthquakes. When a P wave hits a sharp interface in the earth, like say the base of the crust, the interface between crustal rocks and mantle rocks, geophysicists like to call that the MOHO. when a P wave hits that interface, some of that energy, the P wave energy, is going to get converted to an S wave energy. And we can measure those converted P to S waves and build up an image of what the crust and upper mantle look like. So on this image, when you see a red feature like this one, that is telling us about an interface where there's an increase in seismic velocity as a function of depth. That's what we expect to see at the base of the crust. And indeed, this number 1 feature here, this is the base of the crust beneath Connecticut. And then when you see a blue color, that's an interface that actually involves a decrease in seismic velocity with depth. I could talk about this image for the next hour if you let me, but instead I'm going to give you the 30-second version. So here's the MOHO. So we know now very well how thick the crust is beneath Connecticut. It's about 40 kilometers thick here in the west beneath the older Laurentian crust. Much thinner, actually, beneath the accreted Appalachian terrains. It's only about 28 kilometers thick here beneath the central part of the state. You'll notice that this transition from thick crust beneath the Laurentia to thinner crust beneath the Appalachians, it's kind of complicated looking. We have this very sharp transition, and it actually looks like these interfaces are kind of like doubled over or overthrust a little bit. I think this is telling us that the puzzle pieces are fitting together kind of a little jaggedly here beneath Connecticut. Another feature down here that we're kind of excited about, this is a west-dipping interface. Now, this is down in the mantle lithosphere. We think that this is actually a fossil kind of relic of a subducting slab. So this was a subduction zone if you go back, 300 million years. We think that this is actually sort of the fossil signature of one of these subducted slabs that sort of got almost like stuck in the lithosphere while the deeper part of the slab broke off. So again, I could talk your ear off about all of the things that this is telling us about how tectonics worked beneath New England, but the thing I want you to take away is that we can do enormously detailed imaging if we have the right data of the continental crust, and we are just learning an enormous amount about all of the tectonic processes that built this really cool, complicated geology we see at the surface. Okay, so that's vignette number 1. Now I'm going to come back to these red blobs, these unexpected red blobs that we see in the mantle, in the upper mantle beneath the eastern part of the US. Again, this one is the Northern Appalachian anomaly. This is now a different tomography model from a different author, but it shows us the same thing. Slow stuff in the upper mantle here beneath New England, that's the Northern Appalachian anomaly. And then here beneath like Virginia and West Virginia, that's the Central Appalachian anomaly. Now, interestingly, both of these anomalies have been associated with unusual volcanism in the geologic past. So again, we looked at the plate tectonic map. A lot of, most volcanoes happen at plate boundaries. In both of these places, we've had volcanism in the relatively recent geologic past. I'm a geologist, so recent means like 200 million years ago. But here in New England, we have what are known as the Great Meteor Hotspot volcanics. So these are volcanic rocks that are about 125 million years old. We think what happened there is that the North American plate, or this part of the North American plate, passed over what we call a mantle plume or a hot spot. So this is what's happening today beneath Hawaii. We have a mantle plume, hot upwelling rock in the mantle, and the plate kind of moves over it, and you get this time progressive chain of volcanoes. So we think that this happened beneath what is today New England about 125 million years ago. And then in Virginia, about 48 million years ago, which again, to a geologist is like nothing. There was this little blip of randomly, a volcano in Virginia, which is as odd as it sounds. And so this happened 48 million years ago, and we know that from dating the rocks, and that is kind of right where the Central Appalachian anomaly is. So for each of these anomalies, there's been some thinking in the literature about what might have caused them, but we don't really know. And the way to test those models is to collect some really detailed geophysical data. And so that is exactly what we did. So this is another map of the eastern US. So now we're focusing on the CAA, the Central Appalachian Anomaly. The background colors here are topography. Here's Virginia, West Virginia, and Ohio. And I was involved in what we called the MAGIC experiment. You got to have a good experiment name, and MAGIC is a good one. So this was a line of seismometers that we deployed across the Central Appalachian Anomaly. And one of our science goals was to test models that had been proposed to explain it. And in particular, the model that we were focused on testing is a model that invokes what we call gravity-driven lithospheric loss. This is an idea that was proposed by Sarah Matza and her collaborators. Sarah's a geochemist and petrologist, so she was studying the detailed chemistry of these volcanic rocks. And based on that, she proposed this idea that a little chunk of the continental lithosphere, now remember, the continental lithosphere, it's cold, it's old. Because it's cold, it's dense. And if it can kind of overcome the strength of the rock, you can actually, theoretically, get a little drip of the continental mantle lithosphere just driven by gravity because it's dense, okay? So this idea has been out there, but it's sort of yet to be really convincingly shown that this actually happens, especially here in the Central Appalachian Anomaly. So we wanted to test this model, so we went out and collected a bunch of geophysical data. We did several years worth of work to image the Central Appalachian Anomaly. I know full well that there is way too much information on this slide. I'm so proud of this work, I couldn't help but put it all up. But I know it's a lot to take in, okay? So again, the map here, this is the white symbols are our seismic stations. The red triangles are actually where these Virginia volcanics are. And then all of this over here, this is a series of geophysical images, mostly seismic images of the upper mantle. And we did a whole bunch of different analyses. Here, the red colors here, this is showing you where the Central Appalachian Anomaly is. I'm really just going to tell you the punchline rather than all the technical details. But what we found is that the continental lithosphere beneath the Virginia volcanics in the Central Appalachian Anomaly region is thin. The lithosphere there is actually only about 80 kilometers thick, which is really very thin for continental lithosphere. This is in agreement with a lithospheric loss model. So we like the idea that during the Eocene, that's 48 million years ago, there was a gravity-driven kind of drip of continental lithosphere off the base of the continent. Then we had kind of upwelling return flow to replace the drip. That caused the mantle to melt, and that caused the magmatism and volcanism. And then this kind of drip, this hole in the lithosphere, has been maintained over geologic time. So we found support for this gravity-driven lithospheric loss model as a mechanism to, first of all, generate intraplate volcanism, but also to modify, and actually in this case to destroy, continental lithosphere. So this is a model that is sort of, often sort of talked about in textbooks as a possibility. We were really able to kind of catch it in the act here in the Central Appalachian Anomaly. All right, so now my third little research vignette before we get to earthquakes. The Northern Appalachian Anomaly, so this is now the sister to the CAA. Here we are back up in New England. This is a map of seismic stations. So here's New England, and it's a little hard to see. Here's Maine, Massachusetts, Connecticut is down here. And what we've been doing over the last, decade or so is installing several, actually 3 different arrays, dense arrays of seismometers across New England. So here's SeisCon. I already showed you some results from that one. The yellow triangles are the NEST array, and then these blue ones in eastern Massachusetts are the Genesis array. So again, we've been collecting all this really dense seismic data right above the Northern Appalachian Anomaly, with the goal of being able to do very detailed geophysical imaging. And again, as with the CAA, we're trying to test some kind of hypothetical conceptual models. So I've already mentioned that this portion of the North American plate passed over a mantle plume about 125 million years ago. So there are some ideas that maybe the NAA is there because of the interaction between the plume and the continental lithosphere above it. There are also some ideas that come from the geodynamics literature about what we call edge-driven or small-scale convection, which can kind of like almost like thermally ablate the lithosphere above it. And then, of course, we're also thinking about that gravity-driven kind of drip model that we tested for the CAA. So what's causing the NAA? I'm not going to tell you I know the answer to that, but I am going to share some really interesting, hot off the press results. These are actually unpublished results. You saw it here first. This is work by Kim Espinal, who's a former PhD student of mine. She actually just defended her PhD thesis a couple weeks ago. And Kim has done some really astounding, very detailed tomographic imaging of the NAA. So here's her model. I realize that the state boundaries are not showing up great on the projector, but let me orient you. Maine is up here. Here's New Hampshire, Massachusetts, Connecticut. So this is a tomography model that's really focused on New England. And again, because we have such good resolution, we can see details of the structure of the NAA that haven't been visible in previous models. So this is a map view of her tomographic model. This is a slice at a depth of 125 kilometers. And then this is a cross section. So here, this is D prime. So this is basically a cross section through her model from roughly New Jersey up to northern Maine. And this cross section actually goes all the way down to a depth of 600 kilometers into the mantle. So we're getting pretty deep. Again, the red colors, you know by now, that's where seismic velocities are slow. The blue colors are where they're fast, okay? So a few things to see. First of all, Kim gets a very kind of detailed view of exactly what the NAA looks like. It's not this kind of perfect, roughly circular feature. It has a lot of structure to it. And we can see that both in map view and in the cross-section. In the cross-section, here's the NAA, kind of clear as day. It goes down to about 200 kilometers, very clear, slow anomaly. There are also a couple of other slow anomalies that we're not entirely sure what to make of, one here beneath Maine and one here beneath New Jersey. But the really exciting finding here is this guy, okay? So this is, we are calling this, not very imaginatively, the Connecticut fast anomaly. And this is this area of fast mantle. It's this nearly vertical structure, and it extends all the way down to about 600 kilometers in the mantle. So what is this? When we first got this model, Kim and I spent hours in my office kind of puzzling over this. And then we started comparing this image to models that geodynamicists had made of what it might look like if you lose a piece of your subcontinental lithospheric mantle, if it kind of peels off and then sinks into the mantle. So this is a computer model based on physics. And it's a little tough to see the details. The arrows are telling you about directions of flow. But in this model, we have this, this downwelling piece of cold, fast lithosphere. And then over here to the side, we have this upwelling feature that we would expect to see slow, to be slow to seismic waves. This looks to me an awful lot like this image. So we think that we might be, talk about catching it in the act, that we might be seeing a snapshot of a piece of the lithosphere here beneath New England that has been removed and is sinking back into the mantle. So as I said, these are unpublished results. They have to still go through peer review, but we are wondering whether we are seeing the cold downwelling associated with the removal of continental lithosphere, and we think that this is going to tell us about the origin of the NAA. All right, I got maybe 5 or 10 more minutes, and I promised you some material on earthquakes within the North American continent. So here we go. We've seen this map already, and I've made the point that earthquakes mostly happen along plate boundaries. The mostly is doing some heavy lifting there, because we certainly also see earthquakes far away from plate boundaries. Again, this is a talk about the central and eastern US. So this is a map from the US Geological Survey showing seismicity, going back many, many decades. So all of the dots here show earthquake locations. I suspect that this audience will likely be familiar with the New Madrid seismic zone here in the central part of the US. Of course, there was a pair of probably about magnitude 7 or so earthquakes there in the early 19th century. But there are other seismic zones in the eastern US as well. So here we have, this is the eastern Tennessee seismic zone. This is where the Charleston, South Carolina earthquake was back in 1886. We have the central Virginia seismic zone, the St. Lawrence seismic zone up in Quebec. So a big outstanding scientific question is not so much why do we have intraplate earthquakes. We have a general sense that intraplate earthquakes, so intraplate earthquakes, earthquakes within a tectonic plate, we have a general sense that they happen when old faults that were formed a long time ago by older geologic processes, they get reactivated by the kind of far-field tectonic stresses. So we have a general idea that that happens. We don't have a very good predictive framework for why they happen where they do, right? Why New Madrid and not another place here? So we can ask, especially since we have all these beautiful new images of the lithosphere beneath North America, we can ask, are there correlations between deep seismic structure and intraplate earthquakes? And so here I'm showing our trusty tomography model, which at this point you're sick of because I've showed it a bunch of times. This is the depth at a depth of 200 kilometers. And we can kind of compare this image to this map that shows us earthquake distributions. Are there correlations? Meh, I think the answer is kind of a resounding maybe. You can maybe pick out features on this tomography that, might correspond to the Eastern Tennessee seismic zone, but those correlations aren't particularly robust. Now, this is pretty deep in the continental lithospheric mantle, so we might ask, what about the shallower structure? Does that correlate well with where we see earthquakes? Of course, in order to do that, we have to, again, have very detailed geophysical imaging. But I've recently gotten involved in thinking about this question in the context of the 2024 New Jersey earthquake. So for those of us who live in the Northeast, this was a huge deal. This was April 5th, 2024. A magnitude 4.8 earthquake in northern New Jersey. And if you live in a place like California, 4.8, you don't even get out of bed for a 4.8, but for the Northeast, this is a big deal. It was thankfully no injuries and only very, very minor damage. It was very widely felt, though, and this is a map from the USGS Did You Feel It tool. So all of the colors here show where people went to the website and filled out a felt report. So you can see it was felt from, Maine to Virginia and beyond. We felt it on campus at Yale. This is a recording on our seismometer that we have in the basement of the Klein Geology Lab. Beautifully recorded. Here's the P wave, the S wave, and the surface waves. A lot of people on campus felt it. I felt it. I was sitting in my office. It happened at about 10:30 in the morning. Sitting in my office, I felt a little lurch, and I was like, I think that was an earthquake. And then I had this really funny moment where I was like, who do I ask? And then I was like, Maureen, you are the seismologist. You are the one that, So I quickly on my computer looked at the seismic data from the basement, and sure enough, there's the P wave and the S wave, and I said it was an earthquake. So this was very exciting for us. Like I said, a magnitude 4.8 earthquake is a big deal in the Northeast. If you're wondering what my day looked like on April 5th, I got a lot of media requests, so I joked with my kids that I would be signing autographs later. So I sort of felt like a celebrity. I was not the only seismologist who was very busy that day. So I was busy on the day of the earthquake doing media, but I was also busy in the weeks after the earthquake because I was working with several colleagues. This is work led by Jim Burke, who's a postdoc in my group. This is also some unpublished data that you're getting a sneak peek at. But we got involved in an effort led by the US Geological Survey to deploy a very dense array of instruments right around the epicenter of the earthquake. And this is now a geologic map of New Jersey. The earthquake happened right along the edge of the Newark Basin, kind of an important geologic structure. It's a little tough to see the details, I know, but all of the dots here, these are actually all aftershocks to the earthquake. And we have a very detailed aftershock catalog because we have this dense array. So one of the reasons to put out the dense array is to measure all these aftershocks. There are about 200 aftershocks in the catalog. But the other reason to do this is so now we can do some really detailed structural imaging of the crust beneath the epicenter. And this is some of Jim's work. Again, this is in preparation, hasn't been peer-reviewed yet. We're hoping to submit it soon. But Jim is doing some really spectacular imaging, again, using this P to S wave converted wave technique of the Newark Basin. And we can really clearly see sort of the bottom of this sedimentary basin here. this is basically where the fault plane is. It's sort of illuminated by all the aftershocks, and we do see some intriguing correlations with the structure. So kind of stay tuned on that one, but I think that some progress on this question of what controls the distribution of intraplate earthquakes, I think is going to come from detailed studies like this. All right, I need to wrap up. I could do this all day or all night. I'm going to wrap up, and I'm going to leave you with this map. Again, we're going to come back to this map. I certainly hope I have convinced you that continents and the deep structure of continents are really cool things to study. There are a lot of exciting science questions that we don't know the answer to, but also we're making a lot of progress, and especially in the study of Central and Eastern North America. So before I wrap up, just a few acknowledgements. Lots of collaborators on all the work that I showed. I can't put all their names, but I do want to especially acknowledge the students and postdocs at Yale that have contributed to this work. I want to thank everyone at the Linda Hall Library, the Yale, Princeton, and Harvard Clubs of Kansas City, and the Yale Alumni Association for bringing me here and for the invitation and for facilitating the logistics of my visit. And then finally, I want to thank you, everyone in the audience. So first, thank you for coming to the talk. Thank you for listening to me talk about stuff I'm passionate about for 45 minutes. So thank you for coming. But I also want to thank you for your contributions to the American scientific enterprise. And I think it's really important to say this in this moment where the federal science funding landscape is very uncertain, okay? All of the work, every single piece of work that I showed you today was funded in whole or in part by federal science funding agencies. National Science Foundation, the US Geological Survey, NASA, and a bunch of other ones. All right, I hope when I show you these cool results, I mean, certainly I hope you feel excitement and wonder at them, but I also hope that you feel a sense of pride and ownership, because it is American taxpayers that are funding this work and keeping the American scientific enterprise going. So again, especially in this moment where we're all collectively thinking about what the future of science funding is going to look like in this country, thank you all for your role in supporting this. So I'm going to stop there, and I'm happy to take questions. Thanks. Thank you. You're very kind.
All right, heads up. Heads up. We're going to turn the lights on, so brace yourselves. There we go. Yeah, raise your hand. We got time for a few questions. I'll start up front, work my way back.
All right, I went a little long, but I hope we can do at least a few questions. Yep.
Yeah, well, thank you so much for this interesting discussion of our Earth. My question to you is, when you started to talk about the ability to predict where earthquakes will happen.
Yeah.
Maybe how big they'll be so we can be prepared. Like the weather technology now is much better predicting hurricanes, tornadoes, activity. Where is the technology now in terms of being able to predict where earthquakes are, how might be able, and as you go forward, will AI help in expediting that process?
Fantastic question, and I have to say, you have done it. You have used the P word of predict with a seismologist. So the whole question about earthquake prediction, it's a great one, okay? So seismologists and other earth scientists, we've gotten very good at doing what might be termed earthquake forecasting, right? So in areas of the world that have a lot of geophysical instrumentation, which is not everywhere, but in places like California or Japan, we've gotten very good at understanding what the seismic cycle looks like and how much time there is, between big earthquakes. And we've gotten very good at making very good quantitative models that say, this area in California has a 50% chance of experiencing this level of ground acceleration in the next 50 years or something, okay? So that's great, and it's super valuable because it tells us how to build our infrastructure and how to be prepared. But it isn't prediction in the way that most people think about it, which is there's going to be an earthquake next Wednesday, so evacuate the city, right? So there's a lot of scientific thinking about that kind of prediction. Again, that's the P word, and whether that's ever going to be possible. And seismologists, there's some disagreement about this. my own personal opinion, and I don't work in the field of earthquake prediction, my own opinion is I don't think we're ever going to get to the kind of prediction that says, you know, there's going to be an earthquake next week, evacuate the city. What we can do is learn as much as we can about the physics of earthquakes, make the best forecasts that we can. And AI is already helping in that. There's a lot of, you know, fantastic, I mean, AI is like a whole nother talk, right? There's a lot of fantastic use of machine learning and deep learning models and neural networks in seismology that helps us to get there, to you know, the better forecasting. But in my own view, I don't think prediction of that second kind is going to be possible.
Professor Long,
Yes.
a few rows back on your left.
Yes.
I understand some of the East Coast earthquakes tend to propagate faster because the rock is harder. Could that, if there's a big one, end up in more damage or less damage just because it propagates faster?
Awesome question. So the answer is yes. I'm going to qualify what you said a little bit. So the seismic waves, they do propagate a little faster because they're older, colder rocks. And as we've seen, seismic waves travel faster. They're blue on that tomographic image. But also, the other thing that happens is that they propagate more efficiently. So the energy attenuates, that elastic energy eventually gets attenuated into heat and the waves die off. That attenuation process is less efficient in the central and eastern US than it is out in the western US. And some of us are actually talking about this at the reception beforehand. This is the reason why a magnitude 6 earthquake, say, gets felt over a very, very wide area in the eastern US and a much smaller area in a place like California that's near a plate boundary. And that absolutely has implications for damage. The Mineral Virginia earthquake in, I think it was 2011, a magnitude 5.8, there were landslides. That earthquake triggered landslides hundreds of kilometers away from the epicenter, and that's because that seismic energy propagates much more efficiently in the central and eastern US. So you're spot on.
All right, towards the back of the room.
Yes.
Hi. So earlier you said your colleague identified that with this cold downwelling, afterwards the effect is that there's a replenishment with a warm effect. So if with your unpublished findings that in the Northeast there's a cold downwelling, what's the hypothesis of the effect? Is there to be in the next several million years a volcano to occur in the Northeast?
Great.
What's possible?
Terrific question. So absolutely, when we get this kind of return upwelling, in general, when you have rocks at depth in the earth and you decrease the pressure, you bring them up towards the surface, they melt. It's not the kind of melting that we usually think about, right? Like if you're gonna make cookies or something, I don't really bake, but like if I did, and you needed to melt butter, what would you do? You'd heat it, you'd put it in the microwave. In the earth, rocks usually don't melt that way. Usually they melt because they're down at pressure and then that pressure gets released and they come up to the surface. So absolutely, I would expect that beneath the northern Appalachian anomaly, there's probably upwelling flow. We may well be having partial melting of the mantle. So, does that mean that there's going to be a volcano, tomorrow? And let me say this for everybody to hear. It's funny. I was involved in a study of the NAA. This is before we did all of our deployments about, 7 years ago or so. And we did a press release about it, just like, oh, we found this cool thing in the upper mantle beneath New England. And I swear, for a day, the lead headline on the Fox News website was like, imminent supervolcano beneath New Hampshire, and we're like, no, my mom lives in New Hampshire. I'm like, Mom, don't sell your house. So, these are all processes that take place on, millions to tens of millions of year time scale. So just in case anyone is worried, I am absolutely not saying that there's going to be a volcano in New England anytime soon, at least on a human time scale. But it is kind of fun to think about what might happen. And certainly, you go back 48 million years ago to the kind of early mammals living in Virginia. I mean, they were probably pretty surprised that there was a volcano, randomly popping up. So it is sort of fun to think about the possibilities. But in case anybody lives in New Hampshire or has family there, please don't lose sleep over it.
Right in the back of the room on your right.
Yes.
If we believe that the NAA is due partially to a upwelling of the mantle as the plate moves across it, why do we only see it in one spot as opposed to a tract?
Oh, terrific question. And that's a really good, I think, challenge to the plume model. So the idea that like the NAA is there because the plate passed over the plume 125 million years ago, I think is actually kind of it's a challenge to that model that we only sort of seem to see it in one spot. Now, there's some caveats there. You know, we don't have very good imaging offshore because it's not that we have no seismic instrumentation in the oceans, but it's expensive and difficult to put seismometers at the bottom of the ocean. You can do it. I've actually done it, and it's really fun to go out on a ship and do this work. But we don't have very good coverage in the oceans. So it could be that there are anomalies beneath what we call the New England seamounts offshore, which is kind of the offshore continuation of that plume track, and we just don't have good images of it. You know, another idea is, well, okay, maybe mantle plumes, you know, maybe they're a little intermittent and you don't always have the same flux of upwelling material. So there are maybe some ways to get around it, but I think you posed that very well. I actually think that the fact that we kind of just see the anomaly in one spot is actually sort of a challenge to the plume model, which is why I sort of like the downwelling model that we're thinking about right now.
I saw a couple of hands up over here, right? Oh, yes.
I don't think I want to answer a question as to propose a theory.
Okay.
The New Madrid earthquakes of 1811 and 1812 are some of the most mysterious and frightening things that ever happened in American geology. And I have a theory that they happened because the Farallon plate, which is moving under North America, was moving that way, and it encountered the 1 billion-year-old remnants of that hard, dense, failed rift that's in the Mississippi Valley. It was heading for the East Coast. Here were these big things in the way, and kaboom.
There are ideas very much along that line that are very plausible. So there's been a lot of thinking about why is the New Madrid seismic zone there. And there is a whole class of models that basically invokes very deep mantle processes as an explanation for that. So you mentioned the Farallon slab, so just for everybody, this is the slab, what is today the subducting slab going beneath Cascadia. So today we call it the Juan de Fuca plate. You go back, you know, a couple, 100 million years in Earth's history, this was actually a really big plate, as big as the Pacific plate is today, subducting beneath North America, on its western side, subducting to the east. Today, that subducting plate is down in the mid-mantle beneath the central and eastern US, you know, maybe 1,000 kilometers down or more. But there have been studies that have said, what does the mantle flow field look like from that deep Farallon plate? And could that mantle flow field play a role in concentrating stress in the central part of the North American plate? So it sounds a little bananas to think like, oh gosh, this Farallon slab may play a role in New Madrid seismicity. And we don't know that that's the answer, but there are serious plausible theories that do invoke deep mantle processes for that. So a lot still left to learn.
All right, we're past the top of the hour. Let's do 2 more questions. Okay. Yes, Bill.
You know, you've talked about the East Coast. What about Yellowstone? I noticed on your 75 and 200 kilometer topographic maps that there wasn't a lot of activity there.
Yes, oh my gosh, okay, I could give a whole nother talk about Yellowstone, so be careful what you ask. Yes, so there is a whole nother set of amazing stories about what's going on in the western US, including in Yellowstone, which is actually an area where I've worked. I've done some work in the high lava plains in Oregon, which is a little bit to the west of the Yellowstone hotspot. So yes, all kinds of stuff going on there. I'm not going to flip back, but if you remember that tomography model that I showed a bunch of times, actually, if you just glance at that, I think the most the feature that really jumps out at you the most is actually the Yellowstone Snake River Plain volcanism. There is this screaming, slow anomaly beneath Yellowstone that kind of tracing out that Yellowstone hotspot track. There's actually, there's a lot of discussion around, so Yellowstone, we think, is due to a mantle plume, right? Like we're talking about here in New England, except, more recent. There's a lot of sort of discussion in the scientific community about what parts of Yellowstone and other unusual volcanism in the back arc, what we call the back arc, or the Cascadia subduction zone, what's due to the plume, what's due to the subduction zone. So there's a lot of unanswered questions there. But yeah, I know this talk was about the interior of continental plates in Central and Eastern North America. There's a whole nother set of amazing stories to tell about plate boundaries and about, present day mantle plumes.
All right, we'll stay in the back of the room.
One last one.
Let's make this the final question.
Okay.
So I notice with the Earth map, so many large continents.
Yes.
Is that size pretty much inevitable, and I'm an exoplanet scientist, might there be many smaller continental plates on other ocean-covered worlds?
Oh, what a fascinating question. And I don't think we know I know we don't know the answer to the exoplanet stuff, which I'll get to in a second. I don't think we know whether the size distribution of continents, is it inevitable? Do they inevitably grow with time? And we know that supercontinents get formed and then they break apart. So we know that continents break apart. On today's Earth, the East African Rift Valley, I don't have the map in front of us, but the sort of East African, that is the African continent ripping itself apart or getting ripped apart today. So we know that continents can get bigger by bringing them together, and we know that they can get smaller by ripping them apart. I am not sure we have a first order theory about what controls that size distributions. Exoplanets, I'm so glad you asked about this. Exoplanets, so these are the planets that astronomers are discovering more and more regularly that are orbiting stars in other solar systems. So this is outside our solar system. We actually were talking about this a bit after lunch today when I was getting my lovely tour of the library and looking at the exhibit out here. A huge question to me in exoplanet science is, do exoplanets have plate tectonics? So Earth is the only body in the solar system that has plate tectonics. It's also the only body in the solar system that has life, at least today. Those two facts might be related, and in fact, there's sort of a school of thought that says, we know that actually plate tectonics has played a vital role over Earth's history in regulating the Earth's water cycle, regulating the Earth's carbon cycle. Believe it or not, it's actually plate tectonics that keeps the Earth's climate relatively stable over long periods of geologic time. So a big question in exoplanet science is, are there any other bodies other than the Earth anywhere in the universe that have plate tectonics? Does that mean that they might have life? And do we have any hope with the observational tools that we have of being able to tell whether an exoplanet has plate tectonics or not? So a lot of very smart, and I don't work in this area myself, but a lot of very smart people are trying to answer that question, but it's entirely open. The answer is we don't know, which is always where you want to end a science talk, right? Like, great question and we don't know the answer, so let's go out and find it.
Thank you, Professor Long. That was fascinating. I loved it. And thank you all for attending tonight's program. Visit lindahall.org for information on all of our resources and our upcoming events. I want to give a shout out. October 7th, it's a Tuesday evening. Nobel laureate Carol Greider will be here to talk about her groundbreaking research. So thank you again,
Yes.
Dr. Long.
Thank you
and
so much
have
for
a great
having
rest
me.
of
Thanks
your
for
evening.
coming tonight.